Another example. This time I'm given the equations of the asymptotes and the two vertices. So first I'm going to locate those vertices, 3, 2, and 9, 2. Well, if those are my vertices, my center is halfway between them. And halfway between 3 and 9 is 6. So that's the center. How are these asymptote equations going to help me? Well, very simple. Right here is the slope of the asymptotes, and so hidden in there are A and B, if we can just figure out how to do it. Well, what kind of axis do we have here? Transverse axis. Is this horizontal or vertical? Well, it's obviously a horizontal transverse axis. So the x squared term is going to be first. This A, this 3, is the run, and the 2 is the rise. So my box, and I bet you can draw a much better box than I can. The box is going to have a rise of 2 and a run of 3. So there's my asymptotes. And here's my sketch. Once you've got your asymptotes and your vertices, you can do your sketch. Try to use some symmetry and make them look about the same. The problem I stated didn't really require me to make a sketch. It just said find the equation. Well, I should be in good shape to find the equation, because from my work I did with the slopes here, I know that the A is 3 and the B is 2. And I found the center, right? The center was 6, 2. So here goes my equation. And what goes first, the x squared term or the y squared term? Well, it's a horizontal transverse axis, so x is first. So it's x minus 6 squared over 9. Remember, a squared is always under the first term, the term that gives you the orientation of the transverse axis, minus y minus 2 squared, because 6, 2 was the center, over 4, and that must equal 1. So there's my equation of that hyperbola. Eccentricity is also present in hyperbolas, and it has the same definition that it had for ellipses. Eccentricity is c over a. But because of the way hyperbolas are drawn, eccentricity is always bigger than 1, because c always has to be bigger than a. Right? Here's an a, this distance, and c is this distance. So c always has to be bigger than a. And I've drawn this with a horizontal transverse axis, but it would be just as true with a vertical transverse axis. Notice that if the a and the c are pretty close together, that the hyperbolas are more compressed. They're pointier. And if a and c are further apart, the hyperbolas are going to be less compressed and more flattened out. So this is flatter, and this is pointier, for lack of a better term. These are not industry standard terms here. If e is closer to 1, then c and a are going to be closer to each other. And if c is much greater than a, then this ratio is going to be larger and larger, bigger than 1. So e will be a larger number, and that's what causes it to be flatter this way. Okay, so that's a characterization of eccentricity.